Picking up right where we left off, let's get into some examples. Okay, so here we go. First one, the decomposition of ethanol on a alumina, so that's the common name for aluminum oxide, on an alumina surface catalyst was studied at 600 Kelvin. The balanced reaction is shown below. So here it is, decomposition of ethanol. We, just by looking at this and seeing that it's a catalyst, we don't know the reaction order. I want to make sure that's very clear because now we don't have one of these generic examples. We have a very specific example. And even though we've used a catalyst, we need to see data to see what kind of reaction order this is. And here is the data, okay? Concentration versus time data were collected for this reaction, and a plot of concentration versus time resulted in a straight line with a slope of -4 times 10 to the -5th mole per liter per second, which is the same as molarity per second. Okay, that was the evidence that we needed to conclude that this has to be a zero order reaction. Okay, so A, determine the rate law, the integrated rate law, and the value of the rate constant for this reaction. So how did I know that was a zero order reaction? Well, look, zero order reaction. So plot needed for a straight line, A versus T. Slope gives us K directly, and the unit of that rate constant is mole per liter per second. So if we look at this, the fact that they told us that concentration versus time resulted in a straight line, so we can now simply say the rate law is rate equals K. The integrated rate law, I could write this out symbolically. Let's see. Yes, I think I have enough room to just do this right here. So the integrated rate law is C2H5OH at time t equals -KT plus C2H5OH initial. And then the rate constant is that slope directly, and the units are in there already. So I'll just say K equals 4.00 times 10 to the -5th molarity per second. Okay, not too bad. So now, question B. If the initial concentration of ethanol was 1.25 times 10 minus 2 molar, calculate the half-life of this reaction. Okay, so let's go to our equation sheet. So we can see the half-life is A initial over 2K. So let's do that down here. So B. So we know T 1/2 equals, I'm going to just write in ethanol to make this a specific example instead of a generic example. And so that's just going to be 1.25 times 10 minus 5 molarity. And 2 times the rate constant, so 2 times 4.00 times 10 to the -5th molarity per second. So this math should be pretty straightforward. We're going to say 1.25 times 10 to the -5th. Nope, not that one. Try again. 1.25 times 10 to the -5th. Okay, good. And I'm going to just do the multiplication in my head. 2 times 4 times 10 to the -5th is 8 to the -5th. So make that a little bit easier for us. Divided by 8e to the -5. Good. Let's see. I'm just going to check my cheater notes. Oh, wait a second. That's not it. Did I do something wrong? Oh, you know what I did wrong? I put -5 right here. You were probably like several minutes ago yelling at the screen like, no, you did it wrong. 10 to the -2. So let's try that again. So 1.25 times 10 to the -2. Okay, that looks better. So then divided by 8 times 10 to the -5th. Okay, that's the answer I had in my cheater notes over here. So that's 156. And if you look at this, the molarity and the molarity cancel, and I have 1 over seconds, which is a second. So 156 seconds to get the half-life. So, and then question C, how much time is required for all the 1.25 times 10 minus 2 molar ethanol to decompose? Well, there's a couple different ways we could do that. If we were clever and good at taking shortcuts, we would recognize because this is a zero order reaction, there's only two half-lives, right? There's no exponential decay. So that means we get half, 50% of it reacts, then the next half, the next 50% reacts. So automatically, we could just say 2 times 156 seconds, and that gives us 312 seconds. But let's suppose that maybe we're still clever, but we're just not well practiced with this kinetics, and we weren't as confident of just being able to say times 2 on the half-life. There's another way we could do this, and we're going to see that this is the method we want to do if, for example, we didn't have the half-life. Okay, so what we can do now is use the integrated rate law. So I'll say or. We could set up that integrated rate law, C2H5OH at time t equals negative KT plus C2H5OH initial. And I'm going to plug in everything that I know, and I'm going to solve for t. So if we want to say how much time is required for all of it to react, then the ethanol at time t means it's 0. It's all reacted. Okay, so we know K is negative. K is positive, but there's a negative sign for the equation. 4.00 times 10, where did that number go? To the negative 5th molarity per second. Okay, we'll put a parenthesis around there, times T, plus, and then we know the initial concentration was 1.25 times 10 to the negative 2 molarity per second. And so now what we want to do is solve for T. And I can do that by, I'm going to add that whole chunk over and then divide by the rate constant. So that means it's going to be 1.25 times 10 minus 2 molarity per second divided by 4.0 times 10 to the negative 5th molarity per second. And that's looking very familiar to this calculation. It's just missing the number 2. So hopefully you can see that this is going to work out to that 312 seconds. But just in case we weren't so sure or confident and we needed to work this all out to prove it to ourselves, we can do that. Okay, so when I do all that, look, I got 312 seconds. Okay, perfect. And it's important to note, we can do this with second order, we can do it with zero order, but we can't do that with first order, just multiplying the half-life by 2. If this was first order, we'd have to go through and use this integrated rate law. Okay, next example, another video.